Oh, that took long enough. Oh, sorry for the delay. This laptop gets a little finicky sometimes and it likes to crash occasionally. So now that it's done crashing, I did get one email requesting could I go over the discussion board for Organic 1. And the discussion board this week is you've got the reaction of cis 2-methyl 1-cyclohexanol with, I believe it's HCl. Yep, HCl. What's up? Come here. Oh. I know. It's hard to be you some days. All right. You're going to show my video at some point. Can always hope. So when you have this reaction of HCl, you've got a few possibilities, and it tells you that you've got 3. So based on the atomic weights, one of those is an elimination reaction, and this is going to give you the 1-methylcyclohexane. The second are elimination or substitution reactions. But the thing to keep in mind with this one is to remember how substitution reaction works. We have an SN1 and SN2 mechanism. So if you look at the SN1 mechanism, we'll go through this carbocation intermediate. But this isn't a stable carbocation. It'll actually do a hydride shift and will end up producing 1-methylcyclohexanol. What is going on with this? All right, so on my end, I'm not seeing any video. Apparently you can see it on your end, so I'm just gonna keep going and keep me informed in the chat menu if anything's kind of weird. So if you go through the SN1, the only thing you can produce in reasonable quantity here is the 1-methyl 1-cyclohexanol, and that's one of the products you see in the mass spec. The other is the SN2, and if we go through an SN2, that's a stereospecific mechanism, so we end up getting the trans 1-chloro 2-methyl. There, you finally caught up with me. Okay, we finally get the trans 1-chloro 2-methyl cyclohexane. So that's how you do the discussion board this week. It's actually a little bit of a trick to recognize that you have both the SN1 and SN2, but they're going to give you different products. There's no way to get the cis 1-chloro 2-methyl. Like there's not a mechanism that will give that to you. All right, so questions 36 through 30 on the homework and 62, 63, 72, 73 on the homework, and go over page 11 of the study packet. All right, so let's start with a few homework questions. And Julia, if you could just say which packet problems you're interested in doing. All right. So question 36. So question 36 on the 251 homework. So we've got sodium hydride, sodium amide, which is NH2 minus 1, reacting with 2, 4, 1 butanol. So we have an anion and we have two possibilities for these types of reactions. One is elimination, one is substitution. So for the elimination reaction, we're going to abstract the hydrogen. The hydrogen will come down, form a double bond, displace the OH, and we end up getting OH minus plus 1 butene. Another option is substitution. Now, I would guess from this chapter, this is what it's really asking for, is the substitution product. So for the substitution reaction, we end up displacing the OH group, and we end up producing an amine instead. So let me see if I can get that to come up for you guys to see on your end. So I'm going to guess the organic product here is the amine. And when it says inorganic product, basically any anions or cations that are formed. Really? Is it the elimination product? Really? What's the solution to this one? Oh, that's a nonsense question. Okay, let me get rid of that one. That is utter nonsense. So to answer your question, Elijah, about 36, I don't agree with why on earth it would even give you a problem like that. Sodium amide will do a lot of things. Typically, it's used in elimination reactions. It could also act as a base in this case, but yeah, that's kind of a weird question. 37. Hydrogen bromide. This is going to be an elimination reaction, but it's going to be an elimination reaction with rearrangement. So what we expect to see is actually this becoming a secondary alkyl halide. So when we have this HBr, we're going to promote going through an SN1 mechanism. Whatever. Two, three, four. Really? Because you got it in the wrong solvent to make that happen. So this would be another one. I can kind of see their point, but you're reacting with HBr. If you were reacting with sodium bromide, I'd be a bit more inclined to believe their answers. So the answer to 37 is that it's 1-bromobutane, even though that doesn't really make sense. So let me send a note to the publisher about that one. Question 38. One butanol with sodium bromide, sulfuric acid, and heat. This is acidic conditions under aqueous conditions. How much you want to bet they think it's going to proceed through an SN2? Yep, another SN2 mechanism, even though it shouldn't do that. Cool. By the way, organic textbooks are littered with mistakes. Question 62. Ethyl iodide with triethylamine yields a crystalline compound with the formula C8H8N I. Wow, that's hard to read. In high yield. It is soluble in water and polar solvents such as water, but insoluble in nonpolar ones such as diethyl ether. It does not melt below 200 degrees. C. Draw a reasonable structure for this product. Click on the draw structure to launch it. So we have ethyl iodide and we have this amine, and if you count it up, it's going to end up being should end up having the same formula as this plus ethyl iodide. So we've got 6 carbons. Ethyl iodide's got 2. So yeah, this is a combination reaction. Wow, why is this in here? What on earth is going on with their homeworks? This is a Orgo 2 question. Question 62. What ends up happening with this is you end up forming, I'll draw it for you. So the nitrogen will form a complex with the other 3 carbons, or all the carbons in this compound. The reason I say this is odd is that this is actually something we talk about in Orgo 2. This is a massive issue with nitrogen compounds, is that they do displace they will in fact displace halides, and it's a reaction that you can't stop happening. So that would be my guess, is the tetraethylamine. Yeah, why is that question in this chapter? 62, 63. And here you have it contradicting itself. You have OH as a primary alcohol reacting in HBr, and you end up getting a tertiary bromide. So what happens? The mechanism requires development of unstable polycharged. Well, yes, that's the carbocation. The mechanism requires dissociation of a poor leaving group. Yes, that's for your OH group. You don't have steric hindrance that prevents nucleophilic attack. So hold on. You do have a result, and a carbocation results in a methyl shift. What? Stereoelectronic effects results in an anticoplanar rearrangement of the skeletal carbon. You don't have stereochondins preventing a nucleophilic attack. And the OH is a good leaving group. Now, as far as the stereoelectronic results in an anticoplanar rearrangement, I would think not. Yeah, I think that's just kind of a nonsense phrase they've thrown in there. So for question 63, it does require the formation of carbocation. The carbocation results in a methyl shift. It doesn't require dissociation of a pore leaving group. If it was a pore leaving group, it wouldn't form the carbocation. We don't have stereohedrix. That actually doesn't occur because we have a primary carbocation here that rearranges to a tertiary. And I kind of understand what they're saying here, where the stereoelectronic effects results in an anticoplanar rearrangement of the carbonyl skeleton. It's just kind of like a nonsense phrase. 72. The following nucleophilic substitution reaction has been reported in the chemical literature. Predict by analogy what you know about the following nucleophilic substitution reaction has been reported in the chemical literature. Predict the product by analogy of what you know about nucleophilic substitution. So if we're doing nucleophilic substitution, iodine's a worse leaving group than bromine, but let's see if that's what they say is actually happening. Yep, so this is just basically trying to get you to see that not all substitutions of a halogen require an alcohol. We can get substitution of bromine by iodine, and that's what's happening in this case, is that you have iodine displacing the bromine and you end up with this iodo structure. All right, 73. Nucleophilic substitution, again, it's the same thing. You have this O negative here. It's going to replace the chloride. So basically, the rest of this molecule really isn't that relevant. I'm not going to even bother trying to draw it. The solution here is that you end up getting way to not be the least bit approachable there. What you end up getting here is that this oxygen will displace the chlorine and by nucleophilic attack, and you end up getting this ester instead. So Elijah, hopefully that answered your questions about the ones you had in terms of homework problems. Now, Julia's asked about questions on page 20 and 21. So let me bring that up. Oh, good. I actually like this question. So you have the same starting molecule, but you have two different products. One product you end up with a terminal alkene. And one you end up with this you end up with this alkene between the two groups, but you're starting with the same molecule. And the question is, how do you get to the two of them? Yeah, yeah, two of those contradict their own problems, but okay, that's pretty on the par for books. So the thing here to catch is that these are elimination reactions. So they're going to go through an E mechanism. The question is if it's E1 or E2. So if we go through an E1 elimination, so for an E1 elimination, we end up having a carbocation intermediate, and then we abstract a hydrogen. So if we have a carbocation here, it's going to rearrange to give us this product. So if we want to get rearrangement followed by elimination, this needs to be an E1 mechanism. Here we have elimination that doesn't get rearrangement, so this needs to be an E2. Now, in both cases, we're going to want to work with a big, bulky base. My go-to here is tert butoxide. But the question is whether or not we want to drive an E1 or an E2 mechanism. So if we want to drive an E2 mechanism, we're going to go with something that's very low dielectric constant. So we would have tert butoxide in something like diethyl ether. And because we're not stabilizing this carbocation, we're going to get E2 elimination that's going to favor formation of the terminal alkene. If we do something like tetrahydrofuran, THF, THF has a high dielectric constant, and because of that, it will favor the formation of a carbocation. So in principle, by doing this in a solvent that actually favors that carbocation, we can produce this carbocation rearrangement, which will end up giving us this alkene that's between the two methyl groups. Now, Elijah asked about page 11. Below are the pairs of electron ion mass spec data on one corresponding to an alkane, the other is an alcohol halide analog, so propane or propanol or hexane or 3-chlorohexane. Based on the EIMS data, determine which of the following products corresponds to the alcohol. Determine which spectrum corresponds to the data for the alcohol. So this is actually pretty easy. You're just looking for the heavier molecule. So for 1-chloropentane versus pentane, pentane weighs, or chlorine weighs 35.5. So see if you can see it on your end. Here we've got a parent ion about 75-ish. Actually, no, it's hard to see. You would need to blow this up on your side. Look at the scale here. This scale goes to 120, whereas this scale goes to 80. The alkyl halide is going to be the one that weighs more simply because halogens weigh more than hydrogen. So if you've got two compounds and you think one's an alkane and one's the analogous alkyl halide, the one that weighs more is the alkyl halide. Same thing's true of the alcohol. If we add an oxygen in there, it's just going to get heavier. So for all of those, the one that has a bigger spectral range that requires more AMUs, or the one that shows the heavier parent ion peak, that's the one that's the alkyl halide or the alcohol. So the one beneath it, 3-octane octanol versus 3-octane. It's hard to see, but I think it's the one on the left. Some of these you're going to have to blow up. It's just for printing restrictions. I have to put them on here. Put them on here so small. Other questions? The discussion board for this week. So again, with the discussion board, it's a matter of picking up on what mechanism would drive which product. So again, we start with the cis 2-methyl cyclohexanol. And we're going to react it with HCl. And there's a few possibilities here. One is that we can get acid catalyzed dehydration. and we would end up getting the alkene. So that's the first one, and it's meant to kind of be the gimme one that if you look at it, this molecule suddenly gets a lot lighter than the parent molecule. But the question is, what about the other two? And they weigh the same thing, so that should be the tip off there that they're constitutional isomers of one another, or possibly stereoisomers. So if we go through an SN1 mechanism with this HCl, we're going to end up popping off the OH group and producing a carbocation. So if we go the SN1 route, we're going to get a hydride shift, and we'll end up producing the 1-methyl 1-chlorocyclohexane. So SN1 will produce basically won't produce a mixture of cis and trans. It'll only produce this one particular isomer. If we go through an SN2, well, the SN2 is stereospecific. It gives us inversion of the symmetry. So if we go through an SN2 mechanism, the only thing we can produce here is the trans 1-chloro-2-methyl cyclohexane. So these are your three products. These two weigh the same thing. But the reason why we don't get this cis-chloromethyl isomer is that the only way to do that would be to go through a carbocation intermediate, where we could get both the cis and the trans, but because we form a carbocation that can rearrange, we end up actually not getting either the cis or trans. We end up getting that 1-methyl 1-chloro. No, typically they're going to be a lot easier. This is my criticism of McGraw-Hill software, is that your homework can be really all over the place. Their test polls are they're a lot more limited in terms of what they can do. Also, their test polls tend to be a lot less randomized than the question polls that you have for the homeworks. That said, if you do see something that's completely out of left field for your test, let me know. When I do the homework, they show me the questions, but they don't show me the answers. And so a lot of these questions look pretty reasonable if you're just kind of looking at the question like, oh, that would be a nucleophilic substitution. Oh, that would be elimination. So the one Elijah asked earlier where they had the sodium amide, the NaNH2, that actually shows up in Orgo 2, and it's actually used as an elimination, used in elimination reactions. So I'm actually filling up that customer support form right now saying, like, you guys are really kind of contradicting yourself with some of these questions. But the exams are a lot better in that when you pick an exam question, actually they're all multiple choice, so it will show you what the answers are. But yeah, the test questions are going to be a lot more reasonable than the homework, as I would prefer it to be anyway. The difference between the two products of similar weight is one has the chlorine on the same carbon as the methyl group. The other one has the chlorine trans to the methyl group. Now they have the same formula. They're constitutional isomers, but they are different compounds. But the one thing you can't get in this synthesis is the cis-chloromethyl. You have to get the trans-chloromethyl. There's no mechanistic reason why you should be able to get that one. Other questions? Almost done updating the homework. feel like such a whiny customer right now in some of these emails. You either need to change the solvent or change the reaction. All right, almost done. Now to respond to an email with a question. All right. All right, so it looks like all the questions have been kind of answered in the discussion board. I responded to a few emails off to the side. Again, Orgo 1, you got your exam due Sunday at midnight. If you have issues, it's better to email me sooner rather than later. Also, let me know if you see any questions that are completely out of left field. If I look at it and it does look like it's completely out of left field, I'll just give you all credit for it. I will try to be around by email, but that said, I get pretty busy on the weekends, so yeah, I'll try to keep my eye out. But do try to contact me if you're having issues. Otherwise, I will see you all hopefully for the review sessions next week.